this is about some of the constraints that come in designing this flow control system and what that ends up meaning as far as what are actually the kind of the set of viable designs for this semi-automated or flow tracking dose controller. So here are the constraints. The flow has to be laminar in the dosing tubes. Minor losses have to be small. And in order to get minor losses to be small, it requires both that the velocity has to be low and that the minor loss coefficients have to be small. There's going to be a limit to how small you can make the minor loss coefficients because there has to be an entrance to a tube and there has to be a change in diameter at the end where it's exiting. And so there are going to be some expansion or contraction expansion losses. So there's the equation for those losses, that the losses in those tubes are a minor loss coefficient times v squared over 2g, where v is the velocity in the tube. And then the left-hand side is this pi error times head loss. Head loss is what is the total head loss you want to have through that tube. And you need just a tiny bit of that total head loss to be due to minor losses. So pi error might have a value of 0.1, which means that the losses that are due to minor losses could be at most 10% of the total losses. So this is like engineering. In the ideal world, we would just have no minor losses, and then our system would be perfect. But we can't actually do that. There are going to be expansion losses somewhere in our system, and so we just had to set a constraint on them to make them be small enough so that the errors that we get are okay with us. And just a reflection that it took us a number of years to figure out how critical that constraint was. The third big bullet point, dosing tube has to be a reasonable length. It's very easy to design a system where the dosing tube has to be like 7 meters long. And if the dosing tube is 7 meters, I don't know, 22 feet long, that would mean that you would have to find a place in your water treatment plant where there's somewhere where there's a 22-foot long stretch where you can put this straight tube. And that becomes annoying because there aren't many walls that are that long in a small plant. And so finding a design that has dosing tubes that are a reasonable length ends up being a constraint as well. And all of this requires some good engineering. So I'll have, some questions about how do we actually get to a viable design. So I don't know if you'd like thinking in terms of graphs and equations and curves. This is just to illustrate like how this system works. And the graph is head loss on the y-axis as a function of flow rate on the x-axis. And of course, as you increase the flow rate, the head loss increases. So these graphs all go up. So that should make sense. There's more and more head loss as the flow rate goes up. And the red line is the dream world. The red line is what would happen if there were no minor losses. If there were no minor losses and we just had the beautiful Hagen-Poiseuille, it's laminar flow in a long straight tube. That's beautiful. But that's not what's actually happening. So the reality is the blue line. In addition to the Hagen-Poiseuille term, which is the major losses, there's also a minor loss term. And that minor loss term is where the KE, the minor loss coefficient, is showing up in that equation. And that results in a line that is no longer straight, it's curved. So you see how that blue line slowly curves up. And that's the quadratic effect of the Q squared term in that equation, because now there's both a Q term and a Q squared term. And then the way that we're thinking about design, and you could think about modifications to this, but the way we're thinking about design is that we take the point at the maximum flow rate and we pretend that it's linear from there to zero. So the green line is our simple linear model of how we're going to represent this, even though you could think about a better fit, but it's good enough. And that's the green line equation, where we're just making, instead of a quadratic q squared, we're holding the 1q constant, and so the 1q that's being held constant is we're pretending that q max was always equal to the maximum q, and that equation overpredicts the head loss for the entire range, but it's close to reality, and what that makes clear is that what we're trying to do is design a system where the gap between the green line and the blue line is small enough that we're okay. That the plant operator, when they're setting the coagulant dose, they're not going to be frustrated by the dose not responding at all the way they expected it to when they make a change. So that's one perspective on this. Another perspective is, well, what size tubing would you actually use for those doser tubes? The doser tubes, remember, they're the resistors that create the head loss and that create this linear relationship between flow and head. So this graph is maybe a little entertaining version of what happens when you put all the constraints together. So the one constraint was that it had to be laminar, which means that the Reynolds number has to be less than 2,100. And you just take the Reynolds number equation, and the Reynolds number equation has a V in it. And we get rid of that V and instead put Q over A in it. And then we solve for, okay, and A is pi d squared over 4. And then we solve for that D. And when you do that, you get the red equation, that D min laminar is equal to 4Q max over pi times the kinematic viscosity times the maximum Reynolds number. And that constraint, we have to, let's see, that is a minimum diameter. We have to be above the red curve always in order to be in the laminar range. And the next constraint is the blue constraint, which is about the minor loss error. And remember, in order to get minor losses small enough, you have to make the velocities be lower, which means that it helps to go to a larger diameter. A larger diameter will reduce the velocities. And so the minimum diameter that's required to get you a low enough minor loss is also a minimum. So that's plotted there in blue, and we need to be above the blue line. And what's interesting about that is that for the range that's of interest, the blue line dominates. So that was what we hadn't initially realized we were creating this design. Blue line dominates. That's the real constraint. It's not the laminar flow that's the constraint. It's keeping the minor losses small. That is the real constraint. And then there's one more thing, and that is when you go to a hardware store, there's a limited number of different internal diameters of tubing. And so here I've said, let's suppose that we can have the tubing that's in green. So 2/32 of an inch is 1/16 of an inch internal diameter tubing. 4/32 is 1/8 of an inch internal diameter tubing. So like it's a little over 3 millimeters. So those are some tubing sizes, and that creates the green curve. So the green step function says that for flows between 0 and something like, I don't know, 0.8 or something, I could use a 1/16 inch diameter tube. And then at that, once I get to right where my cursor is, the flow is high enough that my minor losses are going to get too large. And so I need to pop up to the next size tubing, which in this case would have been 3/32 of an inch. And that works for a while. And then that tubing starts to have minor losses that are too high. And so I pop up to the next size tubing and keep on going. The next graph just shows a crazy response that you might not have anticipated. And this is, what about the length of the tube that's required to get you the flow through that tube? So we need a tube that gives us 20 centimeters of head loss. So that 20 centimeters is somewhat arbitrary, although it's a nice number. It's nice in the sense that it's the same number that we're using for the linear flow orifice meter. So it's nice to have those two work together. And both of those could be larger, could be smaller. And you should always be wondering, well, what then selected, why was 20 centimeters chosen as the I don't know, the perfect design for aguaclada plants? If we go to more head loss through our linear flow orifice meter and through our dosing system, that ends up meaning that the head loss through the entire plant increases because all the water goes through the linear flow orifice meter. So if we increase the height of that, that's more head loss through the plant, a bigger elevation change across the plant. And that essentially means that the building that the plant is in needs to be taller, because all of the difference in elevation and water in the plant has to be accommodated inside the building. And so if you increase the difference in water between the low end of the plant and the high end of the plant, the building needs to get taller to accommodate that extra height. So it actually costs you money every time you add more head loss to the plant. So that's one reason not to make the head loss really large in the linear flow orifice meter. So then what's as small as it can be and still have it work nicely? I feel like this is kind of a human scale question. Like, it should be nice for an operator to read a number off the side of the entrance tank and know what the flow rate is. It has to be small compared with surface tension effects. There's going to be a surface tension effect on the dosing side where the chemical exits from the dosing tube and drips down and does a free fall. There's a surface tension effect there. So it needs to be something that the height that we have for the head loss has to be much larger than the surface tension effect. So all of that says that 10 centimeters for an LFOM is actually tight. Like, you can make that work for small flow plants, but it's tight. 20 centimeters is nice. If you wanted to have a system with even higher accuracy, you could go to higher head loss. You do get more accuracy as you increase that head loss. Okay, so now we've set 20 centimeters as our head loss. We have a tube that we want to have carrying on the flow that's required for our chemical feed system. And now we need to figure out how long that tube needs to be to get us that target flow rate. And the equation is there in green. And what happens is if your flow is lower, the tube has to get a whole lot longer to create enough head loss. And so that's why these green lines have this crazy, very sharp curve. You would end up having to have a really, really long 1/16 inch diameter tube if you wanted a really, really low flow rate through that tube. So this is going to be, it's going to want to encourage us to try to create designs where we're actually having flow rates that are close to the maximum that a tube can carry, so that the tube can be short. But you understand that if I want to make a dosing tube and I want to put less flow through it than what its maximum is that it can handle, I'm going to have to make it a whole lot longer so that it can still create the required head loss. So how much can you get out of one tube? If we only were to use one tube, and we used a 5 mm diameter dosing tube, which would end up requiring a pretty long tube, but could work. That ends up being about 8.7 milliliters per second of flow. This is basically keeping the minor losses small. And then, this is the QC equation. So this is the equation that a water treatment plant operator has to learn in order to effectively understand what's going on in a water treatment plant. So it's only fair that if you're going to design a water treatment plant, you should also know the QC equation. The QC equation is really mass is conserved, okay? You could think about m dot. The mass rate is equal to the mass rate. That's all this is saying. Q is the flow rate. C is some concentration. And it's got to be the same whether you're measuring the chemical feed system or what's happening in the plant. So there's a little tube that's coming from the stock tank and is going down and then is dosing chemical into your plant where it's blending with the whole flow. So that little tube that's carrying the chemical, if you take its flow rate and its concentration, multiply those two together, that's the same as you get if you take the plant flow and its concentration. Okay, so QC equals QC. So I can take that and I can solve for the flow of the plant given the inputs that I gave, where there's a polyaluminum chloride, the coagulant concentration in the stock and the dose. Notice that there's a big difference. One is 160 grams per liter and the other is 30 milligrams per liter, which is, you want that because you would like it if your stock tank would last for days and not have to be huge. So you want the chemical stock to be very, very high concentration compared to what you're actually using in the plant. So all this analysis suggests that by the time you get to about 50 liters per second, you're going to need more than one dosing tube. So that's the solution, more than one dosing tube. And actually it happens even before 46 liters per second, because even using a 5 millimeter diameter tube ends up being larger than what's really convenient because it ends up being so long. So there's things that can be improved with this system. So designing it so that it is easier to clean, perhaps making it possible to clean it in place is one of the things that I want to be thinking about. Like if we could design a system that they could easily empty out the chemical feed that's in a set of tubes, and they could dump some vinegar in there and let it sit there for a few minutes and then drain it out and then flush it out with water and then replace with the chemicals they're normally using. If they could do that without taking anything apart, that would be a very nice improvement to the design. And another thing that I learned about a year ago that they don't like is they don't like having 6 dosing tubes, each with their own valve, and each need to be taken off and cleaned independently. And so we've had this idea of a bundle of tubes that are inside a pipe. So that's just a sketch of the idea, obviously not drawn as long as it would be. This might be 1.5 meters or 2 meters long, but would have a bunch of small tubes shoved inside of this larger pipe. And the idea is that you're creating all these small flow passages so that you can get laminar flow inside this larger pipe. And that way, when you need to clean it, you would take that whole bundle of tubes offline and you would soak the whole unit at once as one unit in vinegar. You could imagine a system where you have a pipe that's 2 inches in diameter with a cap on the end that's full of vinegar, and you just drop this tube down in that bath of vinegar and clean it that way. That's a design that's waiting to happen. One of the big constraints is that whatever you use, it has to be chlorine resistant, at least on the chlorine side. The coagulant is actually not nearly as difficult. It's just slightly acidic, but it's not corrosive in the same way that the chlorine is. It would be awesome if there were a way to fill up a pipe with a honeycomb structure, right? A hexagonal structure. That would be really, really sweet. but I don't know how to do it. And there's limited materials that actually work with chlorine. PVC is like the best material for working with chlorine. And there's like Tygon tubing is also PVC tubing that's just flexible. So both flexible PVC and hard PVC both work well. If you switch to any other plastics, you're gonna have more trouble. And the only other plastics that are viable are things like Kynar or Teflon-based products, and those are far more expensive. So figuring out how to fabricate this tube in a pipe or whole bundle of tubes in a pipe is a thing that is still waiting for some innovation. Which means that there's more for you guys to help figure out. So my summary of all this related to dosing. We need these two systems, laminar tube flow and for our dosing tubes, and we need a linear flow orifice meter. There are opportunities for improvements on both of those. We need a new LFOM design for flow rates above about 100 liters per second. So once you get up to higher flow rates, you end up with like 18-inch diameter or 2-foot diameter PVC pipes, which are very awkward to work with. And if you think about the idea of the LFOM was that it was just shoved into a coupling that was buried in the concrete in your entrance tank, like the one that you designed. And the idea was that you could actually take that LFOM out of the tank if you wanted to. Once you go to a larger plant, that's not going to be possible because a human cannot lift a 2-foot diameter PVC pipe out of a coupling. It's going to be in there too tightly, and you just can't do it. And the 2-foot diameter, 24-inch, 60-centimeter diameter pipe is also quite expensive. So it begins to make more sense to think of another way of fabricating the LFOM rather than using a pipe. And it would argue for doing something in concrete, making a channel with a weir where you have this, or maybe it's a PVC plate that's an insert into a concrete wall, and you do all the hole drilling in that PVC plate, but it's just like one long flat plate. There's a need for some innovation there. And like I was talking, there's a need for a better dosing tube design for high flows as well. But what's good about it? These devices are robust. There's hardly any moving parts. They need to be designed so that there are no small parts to lose. I'll give another example of things that we learned. Early on, we were experimenting with what connection system do we use to connect between the small tubes and other plumbing pieces. And we got some quick connect plumbing, and those quick connect fixtures have little parts that can come apart. And we just very quickly realized that's a disaster because eventually they do come apart, and then you have little parts rolling around in this big like industrial kind of complex, and they get broken or lost very, very quickly. And so small parts that are easily lost are just not a good idea. It has to be compatible with chlorine, and you got to watch out for every place where there's O-rings. We'd like to use locally sourced materials when possible. So if the Tygon tubing that's available in country is PVC and it's relatively resistant to chlorine, that's a great option. The fittings are actually the real challenging part, like getting the barbed fitting that will connect between the dosing tube and some other part of the plumbing. That's where we're still running into difficulties, and where we think that we end up having to source those here because they're often not available in country. I didn't show you, but we have the equations for the viscosity of both the coagulant. The coagulant viscosity changes quite dramatically as the concentration of the stock increases. I don't actually have any good data on chlorine solution viscosity, but my first order guess is that it's very close to water because the chlorine stock concentrations are quite dilute and they don't have this polymer effect that the coagulants have. And just drilling this home, minor losses have to be minor in this system because minor losses go with the square of the velocity, and we want a linear system. And chlorine is going to deposit calcium carbonate, so that has to be easy to clean. I did learn recently that there are other chlorine compounds that are based on sodium that are also sold as solids. That would be a possible replacement for calcium hypochlorite, but they're not commonly available. They're made in the US, and I haven't seen them in other parts of the world. The other option would be to use bleach. Like, bleach is sodium hypochlorite. You can buy bleach at the grocery store as a liquid. That is actually a really nice chemical to use as a source of chlorine. Many of our local water treatment plants use that instead of using chlorine gas, because people don't like to die from chlorine gas, and so they don't like to use it. But bleach, it's much harder to die from it, so much less hazardous. So bleach is great, and bleach doesn't deposit any calcium carbonate because it doesn't have any calcium, it has sodium. So that would be a great chemical to use. And now you're wondering, well, then why don't we just use bleach instead of calcium hypochlorite? And the reason is because you can buy solid granular calcium hypochlorite, and the amount of chlorine per mass of calcium hypochlorite is much, much, much higher than the amount of chlorine per mass of bleach. And so if you're thinking about transport and the cost of transport of getting this chemical to your site, to your water treatment plant, the costs are lower if you can use calcium hypochlorite. So that's the reason why we're using calcium hypochlorite in Honduras, well, in Central America, and indeed in India as well. And that is the end of that.